Xavier is a very talented high jumper. When training, he can clear a 2.1 meter bar at a constant probability of 3/4. During one training session, Xavier attempts this height 7 times. Let X be the number of times he clears the bar. Remember, if you're dealing with the binomial or binomial experiment, 3 things need to be true. 1, there needs to be a certain number of fixed independent trials. As we can see from this description in this example, what is our number of trials?
7.
It's going to be 7 because Xavier's attempting to do this high jump 7 times. So that's going to represent our n. The second thing for a binomial experiment was that there is a success and a failure. Well, if he's doing high jumping, even if you don't know anything about track, basically what's going to happen is he's going to jump. He's either going to clear the bar or he's going to hit the bar. Okay, so he's going to clear it or not clear it. So you have a success and you have a failure. The third thing is that each time or each trial is independent of the other, which is true. Just because he clears it the first time doesn't mean he's going to clear. That has nothing to do with him clearing it the second time. So this 3/4 represents what for our binomial experiment? Our probability. That probability, our P. So if X is the number of times he clears the bar, then we know that this is a binomial distribution. To refresh your memory, it can be written as your random variable, such that you have a binomial distribution, N and then P, where N represents your number of trials and P represents your probability of success. So all of this at the very beginning could have been summed up in what I just wrote in orange. So make sure that you do know both ways. A says the calculated probability Xavier clears the bar exactly 5 times. What that means is that we're looking for the probability that X is equal to 5, exactly 5 times. Last week, we did it 2 different ways. We did it by hand. We also did it by the calculator. By hand, you use the formula that is N choose X, P to the X, 1 minus P to the N minus X. That was the formula that that you guys learned about last week. Okay, this is how you did it by hand. As we can see from our problem, N is 7, X is 5, because we're trying to figure out him clearing it exactly 5 times. Our probability is 3/4 raised to the X power, which is 5. Then 1 minus P. What's 1 minus 3/4? And then N minus X, so that's going to be 7 minus 5, and that gives us 2. We would type this into our calculator. The 7 choose 5 was derived from our Pascal's triangle. That meant that we were looking at the 7th row of Pascal's triangle, the 6th entry. Remember, it was always one more than that particular number. And then we'll pull that number out. We will multiply it to 3/4 to the 5th power and 1/4 to the 2nd power. That's how we would do it by hand, using a Pascal's triangle to get the number that represents 7 choose 5, and then multiply it to the remaining probabilities. In our calculator, we can do this exact same thing, essentially what the formula implies. We can do it on our calculator. We would go to second bars. We will go all the way to option A. Remember, there's a binom PDF and a binom CDF. PDF means exact, CDF means cumulative, so a range. Since we're looking for exactly 5, we're going to go to binom PDF. Our number of trials is 7. Our probability is 3/4, and our X value is 5. We paste. For those who do not have the option of listing or filling in the list, remember, it's your number of trials, comma, your probability, comma, your X value, and our answer is that. Rounded 3 significant figures, that's going to be 0.311. And that's exactly what we would get if we were to use the formula as well. Questions on A? All right. Then it says find the probability that Javier clears the bar 3 or more times. that is represented as the probability that X is it greater than, less than, greater than or equal to, or less than or equal to?
Greater than or equal to 3.
Greater than or equal to 3. Very good, because it says clears the bar 3 or more times. Now, the one thing about this by hand, that would mean that we are looking for either the probability that X is equal to 3 plus the probability that X is equal to 4, all the way up until we reach the max number of times that Javier is planning to do this high jump. By hand, that could be pretty tedious, especially what I just wrote out, but that's essentially what you're finding. Or you could do the complement, meaning you could find the probability of 0, 1, and 2, and then subtract that sum from 1. Okay, that's another way that you could figure out clearing the bar 3 or more times, doing the complement, finding the probability of him not clearing the bar 1 time and twice, and then subtracting it from 1. All right, this is a little bit shorter compared to the longer one that's at the top. In your calculator, because your calculator only allows you to do technically the probabilities that are to the left of a particular number, you are going to have to do it using this method right here, using the complement. Okay.
Thank you.
You're welcome. All right, and so here we're going to go to second bars. This time we're going to go to Binomial CDF because we're dealing with the range. Okay, it's not exactly one number, it's a range of numbers. For our trials, we still have 7. Our probability is still 3/4, but our X value is going to be what? It's going to be 2. Because again, this calculator, my calculator, a majority of y'all's calculators can only do the probabilities that are to the left of a particular value. It can never do greater than or equal to or greater than. It can only do the ones that are less than. So we go to the next X value, which is 2. We paste it. And that's exactly what the probability of 0 plus the probability of 1 plus the probability of 2 equals. But we want the complement. So we're going to do 1 minus that number. And that is the probability that he'll clear it 3 or more times. So that's going to be 0.987. Xavier's training partner, Aaron, can clear the bar of the same height level at a constant probability of 1/3. During this training session, Aaron also attempts this height 7 times. Okay, so now we have this additional element. We have Aaron. He's still performing a binomial experiment. It's just this time his p-value is 1/3 and his n is still 7. Find the probability that both Javier and Aaron can clear the bar 3 or more times. Okay, this right here is an example of going back to like old school probability. Remember, when we started this last week, I said there might be some concepts from like basic probability that are going to pop up, and this is one of them. The probability that both Aaron and Xavier can clear the bar is an example of intersection. Okay, because we're trying to find probability that both Javier and Aaron can clear the bar. So that's an example of intersection. And because Xavier clearing the bar has nothing to do with Aaron clearing the bar, this is an example of independent events. Okay, so to recap independent events, the probability that Xavier and Aaron are going to clear the bar is basically the probability of Xavier clearing the bar 3 or more times times the probability of Aaron clearing the bar 3 or more times. So we already know the probability of Xavier clearing the bar 3 or more times to be 0.987 ... because you know we never use the rounded answer. Now we just need to find the probability of Aaron clearing the bar 3 or more times. So we're going to have to do the exact same thing we did here, except this time we have to do it for Aaron. Okay. So the probability that Aaron can clear the bar 3 or more times is essentially doing the complement of 0, 1, and 2. I am going to use my calculator here. Then once I find that value, I'm just going to multiply to Xavier's probability. So it's another binomial CDF, 7 trials, 1/3 this time, because remember Aaron was 1/3. X value is 2. But it is the complement, so I have to do 1 minus that number. That's the probability of Aaron clearing the bar 3 or more times. So I take these two numbers, the non-rounded answer, of course, and I multiply them together. So I take Aaron, and this one was Xavier. So my final answer is 0.424. This example is really good because it covers doing an exact, doing a range, throws in a little bit of old school independent events. The one thing it probably doesn't cover is expected value, but expected value is covered throughout all the different distributions, probability, normal, and binomial, okay? Speaking of probability distribution, some of the ones that you guys missed, we're gonna go over them very quickly. I'm just gonna kind of talk you through them because again, you did not get the answers here for this particular homework. So we have a random variable X as a probability distribution function given to us, where X is 0 through 5 and K is a constant that we have to find. Now, recall from the lesson that we did on probability distribution, anytime you're given a function, a probability mass function that you have to work with, essentially what you do is you take your X values and you plug them into the function. When you plug them into the function, you're getting the respective probabilities for each of those X values. So essentially, what you have is you need to figure out what's the probability when you plug in 0, 1, 2, 3, 4, and 5. And then all of these probabilities, all these blank boxes right here should add up to equal what? 1. If this is a probability distribution, then all of these probabilities should add up to equal 1. That's how you had to set this one up to find the value of K, all right? So that literally meant you had to plug in 1 for X, 2 for X, 3 for X, 4 for X, 5 for X, and then 0 for X. I missed 0, okay? But you had to do it for all of them. Now I'm about to do that, not on camera, but that's essentially what you were supposed to do. So then once you plug in all those X values, this is essentially what you have. This is your probability distribution. So what you needed to do was you needed to add all of those probabilities and set them equal to 1. Since all the denominators were the same, I'm adding 16, 32, 8, 4, 2, and 1 to get 63K is equal to 1. And I just realized I had these two backwards. That was my mistake. I had the wrong probabilities in the wrong box, but it is 32K over 243 goes for 0 and 16K over 243 goes for 1. So that's basically 63K is equal to 243. Divide both sides by 63, and your value of K was 27 over 7. That's how you had to do this one. And what was interesting enough, when I looked at the majority of the ones that you guys got wrong, they were all similar. They involved a probability distribution table where you had a variable inside of the probability part, and then you actually had to like solve for that variable, such as this one, okay? was similar. You had a probability distribution table. You had your probabilities for each of these different X values, and you had to find the value of K rounding the 3 significant figures. Well, again, the sum of all of these should equal what? 1. And since you, of course, you're able to use your calculator, what you should have done was you should have plugged K plus K squared plus K to the third plus K to the fourth plus K to the fifth into Y1, and then 1 into Y2 to see where they intersect. Of course, not using K, but using what variable? X, because we can't do other variables besides X in our calculator, okay? But that's how we should have done that one, okay? This was another most missed one by you guys. And so then what you end up getting when you find that intersection point, probably setting your Y max to 1, because we want to see where 1 is. Your Y min, keeping it at 0. Your X max, you probably could have left it at 10, maybe even smaller than that. And then your X min, 0, because since K has to be like an actual value that represents a probability, it can't be negative. So actually, set it to 1, because your probabilities have to be in between 0 and 1. So you could set your Y max to 1 as well. Your answer should have been K is equal to 0.509. Okay? I'm not just randomly going over these just for my health. I want you guys to make sure that you understand the problems that you guys got wrong. So my hope is that you found the paper where you did these problems and you're going back through and making the corrections as needed.
Are we also going to go over the ones that we missed from yesterday's homework?
You guys actually did really well on that one. I mean, I can kind of look and see which ones you guys didn't do too hot on, but overall, you guys did really, really well. If there's one in particular, we can talk about that one. The table below gives the probability distribution of a random variable X. Okay, so again, another probability distribution table where all of these values should add up to equal 1. But there's an additional piece of information. The expected value is equal to 2.3. Expected value is the same thing as the mean of the distribution. To find the expected value, you take the sum of all of your X's, or all of your values you get, where you multiply your X's by their respective probabilities. Okay? So that means that 1 times P minus 3Q plus 2 times P minus Q plus 3 times P, and so on and so forth, should add up to equal your expected value. That's how you had to do this one. All of these should equal your expected value of 2.3. Now, if you're looking, you're like, well, Ms. Anderson, that's 2 different variables. You know what? That's very true. But you also have this as well. So I essentially have 2 equations with 2 variables. So you can do substitution or elimination, or using your calculator if you remember how to do it. It's nothing but a good old system. 1, 2, 3, 4, 5. So your first equation would have been 5p, -4, -3. That's a 3. Oh. Actually, you end up getting 5p is equal to 1 if you add up all these probabilities. -3 minus q is a -4. Plus, yeah, it would have been 5p is equal to 1. So p was equal to 1/5. So then you can actually plug that in to this equation right here, this longer extensive one, and solve for q. Okay. And your value of q should have been negative 0.05. Looking at this one, having reviewed probability distribution, how could I set this up to find C?
You can add them all up and it equals to 1.
Add them all up and set them equal to 1. All of your probabilities. There's just one thing that you had to be aware of and that they did kind of harp on it. The minimum possible value. So they want the smallest value possible for C. So when I do this, what do I do from this point?
Square root.
And what have I always harped on whenever you take the square root in an equation?
It's always possible.
So if I'm looking for the minimum value, what's my answer going to be?
Negative 103.
The negative version. I think some of you guys put the positive version because you forgot about your plus or minus. So be careful on that one. I think this was the last one that you guys had issues with. The majority of you guys had issues with. This one's interesting because it says in a game of dice, 2 dice are rolled and based on the sum of their scores recorded. If the sum is a prime number, then the score is the sum. If the sum of the die is a prime number, score is 0. You have to find the expected score in this game. Remember, expected value, expected anything is your number of trials times your respective probability, okay? In this particular case, we need to create our probability distribution, all right? So first off, let's review a few things. What does it mean to be prime?
You can only get that number by multiplying it by 1 in itself.
So if the sum is a prime number, then the score is 0. So which ones are we not considering?
2.
2.
Oh.
Oh, wait, hold on, sorry. Yeah, so basically what this right here is that this is what's called a sample space. We talked about them a long time ago, but it basically represents the sum of what happens when you roll a 6-sided die, 2 6-sided die. So you have the sum. So we can't include 2 because that's a prime number.
3.
We can't include 3
5.
or 5. 7.
1.
Well, all of these represent like what could happen when you roll the die.
Oh, 1 times 1 equals 1 anyway. So.
But it's the sum, not the product.
Oh, okay.
Any other prime numbers?
11.
11. So in order for us to figure out the expected score, the score only happens if it's a non-prime number, okay? So that we got to figure out, okay, what's the probability of the sum being 4? What's the probability of the sum being 6? What's the probability of the sum being 8 and 9 and 10 and 12? First off, when you roll 2 die, how many outcomes can you have? 36. How many times does the sum of 4 show up? 3 times. What about 6? How many times does 6 show up?
4.
5.
5. How many times does 8 show up?
5 times.
How many times does 9 show up?
4 times.
And 10?
3
And 12.
1.
If this is truly a probability distribution, no, sorry, take it back. So we have our probabilities of actually scoring in this game. So to find the expected score, we need to take the x values and multiply them by the probabilities. These are your x values. You need to multiply them by each of your probabilities and then add them up together. That is how you find your expected score. And then it told you to round to 3 significant figures the answer that you got. And this is how you were to do this problem here. Again, still using the concept of expected value, but this time incorporating it, you had to essentially create your own probability distribution. I didn't make it into a table. I just kind of did it straight out, but you can kind of see the table here. And your answer should have been to 3 significant figure 4.44 points. Yeah. All right, this is a question from your binomial distribution prep work. In a game of dice, each player throws 2 die and finds their sum. Okay, so I went ahead and pulled the same little sum chart from the previous page. Again, this is rolling 1 die. This is rolling the other die, and then the part in the middle represents the sum. So that's an example of a sample space. If the sum is not a prime number, then it is added to the player's score. We're trying to find the probability that a player rolls a die 8 times without rolling more than 2 prime numbers. This here is an example of a binomial distribution because we have our number of trials, which is 8. And then our probability is going to be represented by rolling the die to get the prime number. So what is that probability?
15 over
15 over 36.
36.
Or 5 over 12. Okay. That 15 over 36 represents
the probability of getting a prime number.
the probability of getting a prime number. Okay, the probability of getting a prime number. So if we're trying to find the probability that a player rolls a die 8 times without rolling more than 2 prime numbers, we're essentially finding the probability that x is less than or equal to 2, where x represents rolling a prime number. That's why the probability was 15 over 36. Okay? So we can do this using our calculator, because essentially we're looking for the probability that x is equal to 0, plus the probability of x is equal to 1, plus the probability that x is equal to 2. And me writing this out right here, that is like your method point, because you know we can't put any calculator notation on our paper. So writing out, acknowledging that 1, this is the binomial distribution, what you're actually finding the probabilities of, and then going from there. So second vars, option B, because this is a CDF, I have 8 trials for my 8 times I played. My probability is 5 out of 12, or I could put 15 out of 36. My expected value, my x value is 2. And so then that is my probability, rounding it to 3 significant figures, 0.282. Normal distribution was majority in your calculator, okay? A normal distribution curve was a bell curve, okay? This should look somewhat familiar. You got a bell curve that's symmetric to some x-axis. The x-axis could be grams, liters, height, anything, just kind of depending on the problem. Smack dab in the middle. That value in the middle always represented your mean, okay? So halfway, which means that to the left of the mean was how much of your data? 50%, and to the right was for a total of 100% that's underneath the actual curve. So 100% of your data should lie underneath your bell curve, your normal distribution curve. Now from there, your normal distribution curve was broken up into 3 sections that were spread out by your standard deviation. To the left of your mean, you would subtract 1 standard deviation, 2 standard deviations, 3 standard deviations to get these respective values. To the right of your mean, you would do the opposite. So you would add 1 standard deviation, 2 standard deviations, 3 standard deviations. Now within 1 standard deviation, does anybody remember how much percentage-wise actually lied in between 1 standard deviation?
Wasn't it like 34% for the first one, and then like 12.5 or something? I have it written down in here somewhere.
Now those numbers you're remembering were like that 34% was actually the distance between like one side of the the 1 standard deviation. So if 34% made up from the mean to 1 standard deviation, and 34% made up from the mean to the other side of standard deviation, what's 34 plus 34?
68.
68. So 68% of your data lied between 1 standard deviation. That 12.5 that you ever recall was actually the distance. Ooh, go back. Was actually the distance between like here and here, that 12.5 that you were talking about. Okay. But in total, within 2 standard deviations, it was 95%. And then 3 standard deviations was 99%. If you're like, well, where are you getting this 34 and this 12.5? We'll take those standard deviations, those percentages, and could divide them in half. So half of 68 is 34 and 34. Half of 95 is 47.5. So 47.5 is supposed to lie from, oh my gosh.
Wait, it wasn't 12.5, it was 13.5.
13.5. So 47.5% is supposed to lie from 2 standard deviations to the mean. You just subtract 47.5 and 34, and then that's how we got 13.5 to represent that little space, and so on and so forth. Okay? It's always good to know those, just in case it was like a write down problem, something very short, something very easy. But a majority of our normal distribution problems did not lie on a standard deviation. They actually lied outside of a standard deviation, so we had to use our calculator. We found a majority of our normal distributions using our calculator. We still use the second bars, okay? That's where all the distributions lie, not just, binomial distribution, but normal distribution as well. And we always use normal CDF. We never use normal PDF. Remember, if you think binomial PDF means an exact value, like one value. CDF represented a range. When we were dealing with normal distributions, we were talking about the area from one value to another value. So it was always a range. So we always use normal CDF. Remember, CDF deals with a range. PDF deals with it being exact. So that's why we always use normal CDF. Once you click on normal CDF, for a majority of us, we just have to type in our lower bound of our region, the upper bound of our region, the mean, and the standard deviation. For those who did not have that option, and you know who you are, it was lower, comma, upper, comma, mean, comma, standard deviation, close. Okay? Sometimes we had to deal with probabilities that were like less than a particular value. What will we plug in for our lower bound? Who remembers?
Negative 9 and then E9.
Exactly, we were plugging a really, really, really small number. That's essentially -9 times 10 to the 99th power. So that is 99, a decimal, 99 zeros and a 9, a negative, of course. Okay, so we wanted a really, really, really small number. You remember you got the E by pressing the second button and then the comma button. That's how we got that E there. Okay, and the same thing will work for an upper bound.
When is the instance that you use the E?
Whenever it was something like less than the value, because you wanted a really, really, really small number. Okay, we wanted a really, really small number. The situation like what I drew in the orange, you would not involve the E because you would actually have like a lower bound and then an upper bound that was actually bounded between two values. But anytime you essentially went to infinity, that's when you would have to use the E. Okay, so this one here, your upper bound would have been positive 9 e to the 99th power, because you're going all the way up to infinity on your x-axis. Remember, all of these were x-axis.
Thank you.
You use normal CDF to find probabilities. So essentially the probability underneath your curve from one value to another value. Inverse norm is what we use whenever we were trying to actually find an x value. These particular situations where you were told that the area less than some x value was 25%. Like we already knew what the probability was. We were looking for the x value. That's when we would use inverse norm. Again, second bars took us to this distribution set. Inverse norm was option 3. For us, majority of us, it would be the area, AKA the probability, then the mean, then the standard deviation. For some of you all, you know who you are, you had to actually physically type in area, comma, mean, comma, standard deviation. The one downside about a majority of our calculators was that just like with binomial CDF, with inverse norm, we can only do the probability that's to the left of a particular x value. We can only do the area that's to the left. So if the question asks, what's the probability that you select a person whose height is greater than 65 inches? Well, 65 inches greater than, or actually, let me take that back. We're gonna use inverse norm for that. Let's say the probability was 75% that you selected a height bigger than X. Well, I can't use 75% because that 75% is to the right of that X value. When I go into inverse norm, what am I going to put down for area to represent this situation?
25%?
It'll only be 25% because I can only use the area, or the calculator can only do the area that's to the left of that particular X value. And then your mean and standard deviation will be whatever it is. That was for inverse norm. Inverse norm is used again to find an X value, where normal CDF is used to find a probability.
So you always use the probability on the left.
When you're doing inverse norm, yes. You always use the probability on your left when you're doing inverse norm. Some of you guys do have the option to say left or right. If that's the case, then you just select it and you don't have to worry about this, but the majority of us don't have that option. All right, let's take a look at an example here, okay? You don't have to write this down. I am recording. You can go back and look at it later. I'm just trying to refresh your memory about this. The daily January temperature in Cairns is normally distributed with a mean of 34 degrees Celsius and a standard deviation of 3. One thing that gives this problem away, because in a distribution quiz, you got to know if this is a probability distribution, binomial distribution, or normal distribution. What gives this one away? That's a normal distribution.
Normally distributed.
Normally distributed.
Use your context clues, y'all. Use your context clues, which means you're dealing with normal CDF, inverse norm, that whole thing. For A, we're trying to calculate the probability that a temperature on a randomly chosen day in January is less than 39 degrees Celsius. And speaking of January, how many days are in January?
31.
31. You got to know those type of things. You got to know them. So you got to calculate the probability that the temperature on a randomly chosen day in January is less than 39 degrees Celsius. Well, if my mean is 34, 39 degrees lies on the left or the right of the mean?
The right.
Right.
The right, okay? And we're trying to figure out that it's less than this. What I'm drawing gives you your method points for these normally distributed problems, because you can't write out the calculating notation of normal CDF and blah, blah. Can't do that. That picture, though, shows that you know exactly what you're doing. So I go into my calculator. I go to second bars for all my distributions. And I go to which one? Is it normal CDF? Because I'm looking for a probability. My lower bound is what?
-9.
Exactly. It's a really, really small number. It's the value that's all the way to the left of that normal distribution curve. My upper bound is?
Wait, why don't we use the inverse? If I thought you use inverse when it's to the left.
We use inverse when we're looking for an X value. Here, we already know what the X value is. We know it's 39 degrees. We're looking for a probability, which means we need to use normal CDF. With inverse norm, we use the probability to the left to help us calculate the X value. But if we're already given the X value, we use normal CDF. Our mean is 34, and our standard deviation is 3. So we just fill that in, we paste it in, and that's going to be the probability that the temperature on a randomly chosen day in January is less than 39 degrees Celsius. So that's 0.952. For part B, we're to calculate the expected number of days in January that the temperature will be more than 39 degrees Celsius. Couple of things here. Expected number of days means expected value. To find expected value, we take our N and we multiply it by our P. N represents the number of days in January. And how many days are in January?
31.
P represents the probability. In this case, we're looking for the probability, we're looking for the temperature will be more than 39 degrees Celsius. We just figured out the probability that's going to be less than 39 degrees Celsius. So how do I figure out the probability that's going to be more? How do I find that probability out?
You just
What do I do?
you do the same thing we did. You just change your numbers. Your lower bound would be 39 this time, and your upper bound would be 9, the comma with the 99, and everything else should be the same.
Yep, I can definitely do that. Since I know I'm looking for it to be greater than that, then I can do 39, second comma, 99, everything else stays the same. And I can get this value. What's another way I could have gotten that?
1 minus 0.952.
Exactly, the complement. Because it's already found out what the area was that was to the left. I'm looking for the area that's to the right. So that's going to be 0.0478. If I were to round it to 3 significant figures. So I take that probability and I multiply it by my X value, which is 31, and then that will give me my expected number of days. We do not round unless the problem asks us to round to the nearest whole number. So my expected number of days is 1.48. Last but not least, and this will be us wrapping it up, on a randomly chosen day in January, the probability that the temperature is above T degrees Celsius is 0.7. Find the value of T. This time we're actually looking for the X value. I'm told that at some temperature, the probability is 0.7 if it's above that temperature. So above would mean greater. Here's where I would use inverse norm because I'm looking for my temperature, which is my X value. So I go to second vars, inverse norm. But what do I plug in for my area? Oh, my thing updated.
0.7.
0. Nope.
No, 0.3.
It'll be 0.3 because remember, it's the area that's to the left. So I plug in 0.3. My mean is 34 and my standard deviation is 3. Now, this calculator is the updated version of this. I actually have the option to tell my calculator what tail I want, but a lot of you guys don't have this option. So I'm going to pretend like this tail is not even here. So I go down to paste. And so my temperature would be 32.4 degrees Celsius. What that tail option actually means, like I said, this is the most updated calculator I ever have. All my videos do not have this tail in it. If you have this option, then you don't have to worry about the whole area to the left, okay? Because you can actually tell the calculator, okay, the area is 0.7. I want the right side of that X value, and it gives you the same answer. Okay, that's the beauty and the feature of using the left and the right tail option. But again, a lot of y'all don't have that, so you would do this second to last option here that I did. And that's normal distribution. That's all your distributions. They share some similar things like expected value, but they all have their different methods on how you go about and find probabilities or find X values or find expected numbers and things like that. So please make sure that if you need to, go back and rewatch this video, go back and rewatch some old videos, do whatever you need to make sure that you're prepared for your quiz.